I think people are still joining, but might as well just get started just because we don't want to miss any content. So hey guys, welcome to KIS Academics physics lecture. So I think some of you guys might have attended some of the other seminars that was ran like 2 days ago, and there's going to be a biology one later this afternoon. So my name is Galen. I'm one of the tutors at KIS Academics, and I tutor in physics, chemistry, and math advanced. So that's my role here. And today I'll be responsible for taking you guys through the 4 modules of HSC and some content that I think is important, and walking you guys through some exam techniques, instructions, setting you guys up for the HSC. So here's our team. I think English, business, and math has already been done, and chemistry as well. And I'll be doing physics today, and then biology will be after me straight away, I think, from 2 to 4, I believe.
2 to 5, but yes.
2 to 5, yeah. So I guess I'll introduce a little bit about myself, just so you guys get to know me a bit more. So I graduated from Knox Grammar School last year, so cohort of 2020. I'm currently studying at Bachelor of Commerce and Bachelor of Computer Engineering at UNSW. And professionally, I'm working as a tutor and as well as a basketball coach. So as you can see, personally, I have a twin sister, which is kind of cool. And then in my spare time, I love playing basketball and going to the gym. As you can see from me being a basketball coach, my hobby or my interest lies in the sports area. And the fun fact about myself is that my wingspan is actually shorter than my height. So I think a lot of people would have their wingspan being equal to their height, but mine is shorter. So that gives me a big advantage when I'm playing basketball. Cool, so that's a little bit about myself. So I'll give you guys a quick overview of the content I'll be going through today. So obviously there's 4 modules for physics. And for each module, there's quite a bit of content, but I couldn't cover everything. So I think I picked out some of the important topics or concepts that I'll try and discuss here and get some information for you guys in these topics. So in the first content block, which is the first 25 minutes, I'll be talking about projectile motion, circular motion, and gravitational motion, which is pretty much the gist of module 5. And you guys will then have 5 to 10 minutes break time / Q&A time, where you guys can, I think there's an option on Zoom where you guys can send in your questions and I'll be able to see them and answer them. And then after that, we're going to content block 2, which we'll be discussing a little bit of transformers, motor effect, and a long response, combining a lot of the content from module 6 and a little bit of year 11 content actually. And you guys will find a lot of times that some of the HSC questions actually requires you to know a little bit about year 11 content, which I think is essential definitely to walk you guys through this. And then another 5 minutes, 10-minute break. I think we'll have a longer break here because it's the middle of the lecture. And then we'll go on to content block 3, which is module 7, talking a little bit about Maxwell's contribution, special relativity, and as well as black body radiation and spectrum. And after that, we'll go into our content block 4, which is module 8. I'll talk about the discovery of neutron, Bohr's model, and stars' life cycle, which I think is very important actually to get to know how stars work and their life cycle. Cool, so that's the overview of this webinar. And if you guys have any questions, I'll just get started on content block 1. So how this works is I think I picked out 2 or 3 multi-choices for each module, and you guys have an option on the Zoom, poll option, where you guys can vote on which option it is. So I'll give you guys like 1 or 2 minutes to have a go at this question, and then once answers come in, we'll I'll start discussing how to work these out. So yeah, you guys feel free to have a go at this question. I'll zoom in a little bit so you guys can see clearer. I think that helps. And then once these come in, we'll start talking about it. The question says, in which of the following would the satellite have the greatest escape velocity from Earth? Escape velocity. After a few seconds, maybe give it. Yeah, for sure. Okay. Maybe in the meantime, I'll talk about maybe some techniques for multi-choice. So obviously for actually any type of question, the way I would approach a question is I firstly think about what concept exactly it's testing, right? And from this question, we already know it's going to be escape velocity. And after we know escape velocity, we think about what formulas we'll use for this question exactly, right? What formulas we'll use. And then after that, depending on the difficulty of the question, depending on the type of question, we're either plugging a number or plugging several numbers into the formula and find an answer, or we'll have to sort of eliminate using the process of elimination to try and find the best possible answer. So in this one, I think the hint here is to actually plug in the numbers you have in order to calculate for one specific answer, because it's a calculation question. Okay, so we got two answers here. We got one answer, one person who voted for B and one person who voted for D. Okay. What I'll do is I'll walk you guys through. So the first thing I want to talk about is actually deriving the formula for escape velocity. I wasn't sure how confident you guys were deriving this equation, because when I was learning this, it took me quite a while to memorize how to derive this. But essentially, to derive escape velocity, we have to use the conservation of energy, right? The conservation of energy is essentially energy final is equivalent to energy initial. Is that okay, my writing? It's kind of blurry. I think I'll switch to green, might be better. Oops, doesn't allow me to. That's okay. So energy final equals to energy initial. And in this context, or in HSC in general, we're mainly talking about the change in potential energy, right? And that's equivalent to the change in kinetic energy. And we've explored this concept in year 11, where when we bring an object from some height downwards, we're changing the height and we're converting kinetic energy, we're converting potential energy to kinetic energy, okay? So that's the concept here we use to derive escape velocity. And then following this, we'll break this up into two parts. So the first one, for changing potential energy, we have the potential energy final minus potential energy initial. That's this component here. And then that's equivalent to the negative of KE final minus KE initial. Okay, so then after that, we can plug in the equations for these. So for gravitational potential energy, we know is the equation negative GMM on R. That minuses another minus GMM on R. So be careful of the two minuses there, which will make a plus. And then that's equivalent to, I'll keep the minus in front, KE, which is half V final squared. Because for kinetic energy, the only thing that's actually changing is the velocity. So that's why I indicated final there, minus half mv initial squared. Okay, so then to simplify this a little bit more, we can cancel out these to a plus, and then everything else is fine. So now the next thing to think about is what actually happens in an escape velocity, right? So what is escape velocity? Escape velocity is the velocity required in order for an object to escape its orbit, right? To escape its orbit. So currently, think about a planet is rotating around another planet. And in order for this planet to escape the orbit, it has to travel in a certain amount of speed in order to escape that planet. And this is what we call an escape velocity. And in order to do that, this planet is going to travel infinitely far away to a point we call infinity, right? And at that point, let's think about the implications of that. So at that specific point, what's our potential energy? our potential energy is going to be 0 because we've learned that the point where we define as infinity, potential energy is going to be 0. Okay, so what does that mean? What that means is that potential energy final is going to be 0, right? So this here is going to be 0. Okay, so this leaves us with just G mm on R. Okay, what about kinetic energy? What's the speed at infinity point? It's infinitely far away. It's going to be 0 as well, right? It's going to be 0 as well. So what that means is this component here is also 0. And then since there's a minus here becomes a plus, so we have half mv squared. Okay, and now we can rearrange the equation for v squared is equivalent to 2 gmm on r. V escape is equivalent to root 2 gmm on r. Okay, 2 gmm on r. So that's the equation here, and all we need to do now is to plug in the numbers into the 4 different options there, right? And after we plug in the number, the correct answer here should be D. So we'll plug in G, gravitational constant, radius, which is R. We can keep that constant there, and then we have mass of Earth as well as the mass of the satellite. Okay, cool. So that's this question. Are there any questions? No. Okay, so let's move on to the next question. Give you guys another 1 or 2 minutes. I've got this. I'll zoom in a little bit more. You guys can see it. Okay, I think that's all right. So the question says a rocket returns to Earth to rescue after launching satellites using its engines to make a controlled landing. The rocket, having a mass of 7,800 kilograms, is on approach to the ground, traveling horizontally at 20 milliseconds, 20 meters per second as shown in the diagram, when the engine thrust is changed to 90,000 newtons. And we have to pick which diagram best represents the trajectory of this change of thrust. Okay. So one thing to think about here is to think about projectile motion concepts. Where we analyze motion in 2 planes. We analyze motion in the horizontal plane as well as the vertical plane. Okay, so here we have the horizontal plane as the rocket traveling to the right at 20 meters per second. So that might be something worth thinking about.
I'll give you another couple of seconds. If you're not sure, still give it a go.
Yeah, just a couple seconds left. Once Emma reviews the answers, I'll start going through this one. Okay, cool. So one answer again, and we got option D. So that's actually the right answer. Let me now go through this question. So essentially, what we need to consider here is we need to consider the forces as well as acceleration. Okay, so initially, do we agree we have a force downward of mg, right, by the rocket, because the rocket has some sort of mass and it's under the influence of gravity. Okay, so what this is 7,800 kilograms times gravity, which is 9.8, and this actually gives us 76440 newtons downwards. Okay, so this is the current net force on the rocket. Okay, I see it clearly. Okay, that's okay. Okay, yeah, so that's the current net force downwards on the rocket. Okay, so now what we have is we have a change in thrust, and now we have a force of 90,000 newtons going upwards. We have a force of 90,000 newtons. upwards. Okay, so now if we were to draw the free body diagram again, we'll have mg and thrust there. Okay, so as you can see, if we were to calculate the net force now, we'll have to do 90,000 minus 76,440 to get some sort of net force. Okay, because the forces in different direction, the signs for them would be different. Okay, so what this actually gives us is we have a net force going upwards at the end, right? And from Newton's second law, F equals to ma. If we have some force, we'll have some acceleration, right? And if we have some sort of acceleration, if you think back to projectile motion, we have some sort of acceleration, the upwards velocity is going to be constantly increasing, right? Constantly increasing. And if it's constantly increasing, what that means is the trajectory is not going to be something linear like that, right? Or like that. It's going to be some sort of parabolic trajectory, right? And as we know, the net force is going upwards. Therefore, we can conclude that the trajectory is going to be some sort of parabolic shape like that. And that sort of informs our answer as option D. Okay. Cool. Are there any questions? Q&A. There's a question here, I think. Alex says, am I the only one in the meeting? No, I think there's quite a few other attendees here. So, all right, cool. Let's move on to the next question. Because we only have 5 more minutes left. I want to get to a long response. Yeah, I'll do this question, projectile motion question. So this is one of the 2020 HSC questions that I did. Kind of unique, not your ordinary projectile motion where they give you a diagram, some sort of platform, shooting of a cannonball down, and some sort of stuff like that. It's more of like a graph where you have to analyze and interpret, find information you need, and then go on and finish up the question. Okay, so the first thing here, what we can do is we can list out all the information we have. So what do we have? What information do we have? Do we have UY? So UY is the initial vertical velocity in the vertical component. Do we have that? That's the thing we need to find, right? We need to find UY. What else do we need to find in order to find the initial velocity of the projectile? We need to find UX, right? UX. We need to find UX. So for this question, it's really good if we're working backwards. Looking at the question, we need to find the initial velocity of the projectile. We need to find the initial velocity of vertical component and the horizontal component. And once we find that, we're able to find the initial velocity in general. Okay, so we need to find these two components. But what do we have? We have SY as 44, right? Because if you see on the graph there, at this point, it's actually 44. Okay, 44. And what else do we know? What other information can we draw from this graph? Thinking about projectile motion concept. When the projectile travels to the very top of the trajectory, what's its vertical velocity? What's its vertical velocity? It's got to be 0, right? So Vy is 0. And these two is when at max height. Okay, so now we have the information we need. What we can do is we can try and find the components we need. So let's first find UX. UX should be pretty straightforward because we have the range equals UXT formula, right? We have time, we have range, and we need to find the UX. Okay, so 130 is equivalent to UX times time, which is 6 seconds. So UX is equivalent to, we calculate that, 130 over 6, which is 21.6 recursive. Right, so now UX. How do we find UY? This is the important part here. There's 3 kinematic formulas we have. V equals to U plus AT, S equals to UT plus half AT squared, and V squared equals to U squared plus 2AS. So we have the displacement that SY equals 44. So that instantly rules out that first option because we don't have displacement there, right? So do we use the second one or the third one? Well, in the second one, we have UT, and UT there means UI. We don't have UI, we're trying to find UI, right? So we can use the second one, but the third one actually is a lot easier to use because we don't have to find a quadratic. So what we do is we know V is going to be 0 and U we can find. So what we can do is we can rearrange to find U squared is equivalent to -2 times 9.8 times -44. Okay, times 44. So here the negative actually doesn't really matter because our gravity or our U squared is there, so it doesn't really matter. So at the end, we'll achieve U is equivalent to, no, this is UY actually. If I quickly type that in, it should be square root of 2 times 9.8 times 44. 2 times 9.8 times 44 gives us around 29.3. 29.3. Okay, now we have both components. We can use tan theta equals to uy over ux, which is equivalent to 29.3 over 21.6. Okay, 29.6. Find the angle, and then this will be equivalent to some theta. And then last thing we need to do is to use Pythagoras Theorem to find the actual initial velocity here. You find the initial velocity here. So what we need to do is uy squared plus ux squared is equivalent to u squared. Okay, equal to u squared. A squared plus b squared equals c squared. So u is equivalent to square root of uy squared plus ux squared. Okay, so that's the working out for this question. So the main takeaway here for this question is that we need to draw information out of the graph, and we needed to use one specific point on the trajectory, which is where the trajectory reaches max height. At max height, Vy equals to 0. And then we also have the displacement there, right? And then since the question gave us a range, we're able to find Ux, and then we can use kinematic equation to find Uy, and ultimately find the initial velocity. Okay, cool. There's one question here. Let me quickly look. We could have also used S equals to UT plus 0.5 AT squared by using 3 seconds instead of 6 because first half. Yeah, exactly. You can definitely use SY equals UIT plus half AT squared because we have all the information for that as well. So definitely, yeah. The only problem with that is it's a little bit more complicated, the calculation. But yeah, spot on. You can definitely use that. Cool. Is it Q&A time now, Emma, or should I keep going?
Up to you. Depends on what you want.
I think we'll keep going just because we have 5 more minutes. I think it's better if we just keep going through content. Yeah, so I'll quickly go through this question as well. So this is one of the gravitational questions that actually gets a lot of people, I think. So the question says the orbit of the comet is shown. Account for the changes in velocity of the comet as it completes one orbit from position P. Okay, counts the changes in velocity of the comet. Okay, so one question for you guys is what concept or what area of topic is this question testing? There's one specific area this is testing. You guys can put it into Q&A if you guys want, and I can have a look.
We've got one response saying Kepler's laws.
Yep, exactly. Kepler's law. That's exactly right. So this is assessing us on Kepler's second law, right? And what this law tells us is that equal time sweeps equal area. Okay, equal time sweeps equal area. That's the law here. Okay, so now we have that law in mind, we can sort of try and explain the changes in velocity, right? So there's two ways to go about this, and I'll sort of give a little bit of insight on how to enhance your answer a little bit. This is something I learned during my HSC to enhance this specific point. So obviously the first thing we can talk about is if the comet is far away from the sun, what that means is it's going to sweep more area. It's going to sweep more area with a little bit of movement, right? So what we can do, you can draw a diagram to sort of indicate that, like, okay, sun's here, comet's here. If the comet moves from there to here, that's actually the area covered, like, covers a huge amount of area, right? Compared to if the comet moves the same amount of distance, which only covers this amount of area, right? So what that means is we can explain this saying when the comet is far away from the sun, it's going to travel a bit slower, well, a lot slower actually, a lot slower, because it's going to sweep a lot more area in the same amount of time. Okay, so we can explain the first dot point, saying as the comet sweeps more area when it is far away, it will travel slower, and vice versa, okay? So that's the first thing you can talk about here. And by having a diagram there, it will indicate clearly to the marker that you understand what it means by covering a bigger or larger area when it's further away, okay? So by defining Kepler's second law and explaining this with a little more detail, you're able to score 3 out of 3, right? But something I always talk about here is I always talk about the velocity vectors, right? So this is something that might be new to you guys. So I'll show you what this means. So when I'll draw a new diagram actually, I think it's better. When the comet is here, the sun there, the centripetal force is going this way, right? Because it's rotating around the sun. It has some sort of centripetal force, okay? So as you can see, it's pointing straight to the center. But as this comet rotates this way, when it gets to about here, if I drew the centripetal force, it's something like that, right? And what we can do here is we can break this component up into its vertical and horizontal component. And it's going to look something like this. Okay. And what that means is this component here is the velocity, right? Or more precisely, tangential velocity. And this is what defines how fast the comet is traveling. The comet is traveling. Okay. So as this goes closer and closer, what happens is the component of the force contributes a larger component to the tangential velocity compared to the centripetal force. So somewhere here, we have a huge amount of component going tangentially and some component going inwards. Okay, so what you can say here is as the comet travels closer to the sun, its centripetal force contributes more to the tangential velocity. Okay, and then after this, it might be worth for you to give a final summary talking about thus, as the comet travels from P towards the sun, its velocity will increase, and as it travels from the sun back to P, it will decrease. Just as a summary to sort of back up everything you've said. Okay, back up everything you've said. Cool. Any questions at all for this? Hope I've explained this concept well. I'm aware that the writing is kind of blurry or a little bit like not clear. I was using green before, but it's not allowing me to use green anymore. I think I need to log in again. I might do that after the next break. So I can use green, which is more clear. But if you guys have any questions, I'm happy to move on to the next one. Okay. All right. I'm gonna move on to module 6, but before that, maybe I'll give you guys a 2-minute break so I can I can log in. Actually, let me just stop sharing screen for 1 second. Yeah, so you guys feel free to take a 2-minute break. And I'll be back after I sign in.
And also, just while Galen is doing that, I know you can't see me, but I'm the events manager at KIS, and Galen's way too modest to say this himself, but he is an amazing tutor. As you can see, he knows his stuff. If you're looking for a tutor in the next couple of weeks, just leading up to the HSC, even if you just want to do one lesson with him, he has some availability, but it is quite limited. So get onto that when he puts the QR code back up, and check out his profile.
I actually have no idea how to log in. I just logged in before, but when I imported this new PowerPoint, it's not letting me. Oh, okay. Let me just say there's a copy there, maybe. File app, smooth. Oh, there we go. I think I did it. Okay, let me go back to this slide here. Okay, it's allowing me to use green now. Beautiful. Go here. Start sharing screen again. Let me know if you guys can see it clearly. But now I can use green, which is, I think, better. Yeah. Okay. All right, let's move on to module 6. So module 6 is one of the modules that takes quite a decent amount of understanding, especially in the topic of induction. Okay. And this first question is on induction. So I'll give you guys 1 minute to have a go, 1 or 2 minutes to have a go at this question. And then we'll talk about it straight after. So think closely to, again, magnetic induction. Okay, magnetic induction.
Okay, people seem a little bit more confident with this one, so we'll give it another couple of seconds just if anyone else wants to answer. Can you see those results, Galen?
Yeah, I can. People chose D. People chose D. So we have 3 responses, and people 3 responses are D. So that's exactly right. That's exactly right. I'm actually kind of curious on how you guys work this out, because I do want to see the train of thought on you guys. So maybe in the meantime, you can type in your train of thought, and while I'll explain how I would approach this question. I think that'll be good. Okay, so firstly, let's quickly read the question again. The diagram shows 2 coils wound around a solid iron rod. Initially, the switch is closed. And then the question is, opening the switch will cause the galvanometer pointer to either remain at constant reading, move from non-zero reading to 0 reading, move from 0 to a non-zero where it remains, or move from 0 to non-zero and then back to 0. Okay. So the first thing we need to consider here is we need to identify which concept this is. And obviously, as I talked about before, it's the concept of magnetic induction. Okay, magnetic induction. So what that means is, while there's a current flowing in one coil, it's going to induce a magnetic field in the first coil there, where the switch is located. And then when there's a magnetic field, it's going to be changing flux. Second coil experiences a changing flux, and therefore EMF, and so on and so forth. Okay, so by looking at that diagram there, what we need to do is we need to identify which way the current is flowing. Okay, so from the diagram there, we can see the current is flowing. From your perspective, it will be going back first and then up towards you again. So it's sort of this circular loop, but first thing is going back and then towards you. Okay, so if you represent that with your fingers, it'll be curling your fingers upwards like that, curling fingers upward like that. Okay, and from a rule you guys might have learned called the right hand grip rule, where your fingers represent the direction of the current on a solenoid / coil, just like that example there. Your thumb will be the direction of the North Pole. Your thumb will be the direction of the North Pole. Okay, from the North Pole. So what that means is it induced a magnetic field that's going to the right. That's going to the right. Okay, and there's actually two ways to do this question, two ways to think about it. Okay, so the first way is to utilize the concept of South Pole to oppose North Pole. And that method is really good for stuff like the solenoids or AC induction motor. However, in some questions where it's like, for example, moving the coil across a certain area, that's going to be a little bit more harder to determine the direction of the current, just because we can't really use our hand to determine the direction. Okay, but for this question, I'll just explain using the right hand rule. So with Lenz's law, what it says is, according to conservation of energy, the direction of the current induced in the second coil is going to flow in a direction that induces another magnetic field to oppose the initial change in flux. Okay, initial change in flux. So if we have a North Pole there, how do we oppose that? How do we oppose that? We have a North Pole there. So we increase flux to the right. We'll increase flux to the left, right? We put a North Pole to oppose this. So two north will repel each other. Okay, so I put a North Pole there, we're going to induce a current in that second coil. But this is not the point. The point here is it's going to induce a current anyway. But what we need to figure out is we need to figure out which option it is. Okay, so obviously it's not going to remain a constant reading because we induce a new current. So A is ruled out. So A is ruled out. B moves from non-zero reading to zero reading, which is also not true because it actually moves from the zero reading to a non-zero reading because there's no current initially, and then we induce the current through magnetic induction, which therefore caused the galvanometer to measure current and therefore have some reading on there, right? So B is wrong. So we need to determine if it's C or D. So C is pretty much saying that once the current is there, it stays there, but D is it goes back to zero. Okay, so something we need to identify here is pretty much what the source of voltage is or the power supply is here. Okay, so in order for the current to remain there, we need to be constantly changing the magnetic field, because only a changing magnetic field will induce an EMF, and only an EMF will induce a current, right? Only EMF will induce a current. And since this is a DC power, it's not going to be a constant changing flux. I'm going to constant changing flux. Okay, and therefore, without a constant changing flux, there's not going to be an EMF induced after it initially goes from zero to some sort of voltage and some sort of current. Does that make sense? So I'll explain one more time. The reason why it goes from zero to some reading is because we turn on the voltage and some current is going through the coil, in the primary coil, in the first coil, right? And that's going to induce a changing magnetic field. But once that voltage reaches its peak or reaches a certain number, it's not going to change anymore. And that means the current will stay constant. A constant current means a constant magnetic field. A constant magnetic field means zero changing flux. Keep in mind that the B field is still there. It's just not changing, right? For EMF, it's only change in magnetic flux, okay? And therefore, it's going to go back to zero because there's no EMF and no current. Okay, there's still voltage and still current flowing in the primary coil, but there's no change in flux anymore. Okay, cool. Let's move on to the next question. I'll give you guys another 1 minute to do this one. I think you guys can see it, hopefully. Not sure. I think Emma just left. Let me quickly check. So I can bring out the polls for you guys actually. But yeah, feel free to have a go at this question. Have a go at this question. Give you guys another 1 or 2 minutes. Oh, Emma is back. Okay. I'm just giving them another 1 minute to do this multi-choice. So Emma, if you bring up the poll again, will be good. Yeah, thank you. So this question is examining us on our understanding of electric field and gravitational field, purely on the field and its implications. So once Emma reviews the answers, I'll start going through this question. Cool. So one answer who chose D. Okay. Cool. Let me go through the answers and I'll review if this person got it right or wrong. Okay. So a little bit of a tricky question, kind of really tricky. When I first did this question myself, I got tricked as well. Okay. So essentially, we have a trajectory of particle with charge Q with mass M fired horizontally into the vacuum chamber where it falls under the influence of gravity. So first thing we have is F equals to mg. Hope that's a little bit clearer. Yeah, green looks a bit better. F equals mg, right? And then the experiment is repeated with a uniform vertical electric field applied such that the particle travels the same horizontal distance d but strikes the upper surface of the chamber. Okay, so what this question is asking us to do is to find a magnitude of the electric field using a formula or equation. Okay, so we have the force on the particle with gravitational field. We can also have the force on the particle on electric field, which is F equals to Q times E. Okay, so what we need to do now is we need to figure out the ratio between these two. Okay, so if from gravity it's going down all the way to D, and then after we apply the electric field, it goes up all the way. How much sort of proportion, if I sort of named this proportion as 1, how much proportion did we travel after applying the electric field? We traveled 2 proportions, right? We traveled 2 proportions. So what that means is the electric field, the force on electric field made us travel 2 proportions compared to the first one. Okay, so now this is the tricky part. If we were to compare just this 1 proportion to the electric field, how much less is the electric field, or how much proportion is the electric field? Is it 2 times or is it half times? 2 times or half times? So so what I mean is, if I wanted to make this particle travel the exact same trajectory, but using the electric field here, how much less is the electric field? It's going to be half, right? It's going to be half because 1, it's going to make the trajectory travel a full amount, which is 2 proportions, or 1 here and 1 here, right? So to travel 1 proportion is half QE. Okay, so therefore, if we equated F of G equals to F of E, we can do mg is equivalent to half QE. I'll emphasize this one more time. So from the gravity, we're able to travel 1 proportion, right? But if you want to use the electric field to travel the same proportion, all we need is half the amount of force. because 1 QE will make us travel from pretty much here all the way up to top. Okay, because it's right now here and we made it all the way up there. Okay, and now all we need to do is rearrange the formula to find electric field. So E is equivalent to 2 times mg over q. And that gives the answer of D. So whoever voted for that option there is spot on. But I hope this makes sense, which is quite tricky because initially what I did was I did mg was equivalent to 2QE. 2QE because I was thinking in order for the particle to travel twice the amount, I need to use twice the amount of force. But that wasn't the case. It's actually half amount of force of gravity. Okay. Cool. Any questions at all? I don't think we have any. Okay. Let's move on to the next one. So we have a transformer question. So transformer, the reason why I think it's quite important is because it utilizes the concept of induction, right? And on top of that, there's some other implications on transformers, such as conservation of energy, some day-to-day applications, and so on. And that's why I think it's really important, because if you understand transformers, that means you understand induction. And that's pretty much the big proportion of module 6. Okay. So let's go through this question. So part A, we have a step-up transformer is constructed using a solid iron core. The cores are made using copper wires of different thicknesses as shown. The table shows electrical data for this transformer. Explain how the operation of the transformer remains consistent with the law of conservation of energy. Include relevant calculation in your answer. Okay, so what's the first thing we do? So maybe I'll underline a few key terms here. Conservation of energy and operation, and then relevant calculation. So 3 things here. So the first thing we do is to define what the law of conservation of energy is. Law of conservation of energy is the energy is that energy initial is equivalent to energy final. Whenever the question asks about conservation of energy, always define this first. It's going to guarantee you like 1 mark, no matter what. And then you can list the equation here. E final equals to E initial, right? And then you can say in a context of transformers, we are talking about power. Okay, so what that means is power out is equivalent to power in. That's the key here. Power out equals to power in. Okay, so what that means is what's the formula for power? VI, right? And in terms of a transformer context, what's P out? P out is the voltage in the secondary coil multiplied by the current in the secondary coil, right? And that should be equivalent to the voltage in the primary coil times current in the primary coil. Voltage times the current in the primary coil. Okay, so now all we need to do is to verify this and show that it's consistent with the conservation of energy. Okay, so if you do some relevant calculations, Vs times Is is equivalent to 50 times 9, which is equivalent to 450 watts. Okay, or joules. Okay, but if we used Vp times Ip, they gave us 500 joules per second, which is equivalent to watts. So these 2 units are interchangeable. Okay, as you can see, one is 500, one is 450. And why is that? shouldn't it be P out equals P in? Well, if you think about transformers, we think about a ideal transformer as a transformer that doesn't lose any sort of energy at all. But that's impossible in real life because we have wires that cause heat loss. We have the solar iron core experiencing some change in flux and therefore also experience heat loss because of eddy currents. Okay, so what we can say here is we can say there is a 50 watts power loss, which is caused by some heat loss / energy loss to demonstrate its consistency to P out equals to P in a non-ideal, or this could be replaced as real world maybe, transformer. Okay, so that's how you approach this question. Firstly, define laws of conservation of energy. Secondly, talk about the context of a transformer, which is power in equals power out. Do some relevant calculations as specified in the question, and then give an overall conclusion and link how it's consistent with the conservation of energy. Okay. Any questions at all? No Q&A so far. Cool. Next question says here, explain 2 modifications the transformer would improve its efficiency. Maybe I'll let you guys have a go at just naming any modifications. You don't have to explain, just name the modification there and see what you guys can come up with in the chat or Q&A. I think either one works. I'll give you guys 30 seconds to do this. Yeah, just name or come up with any modifications you can make to improve the efficiency of this transformer. Improve the efficiency of the transformer. Laminate the core, cooling systems, cutting up iron core to reduce eddy currents using soft malleable iron core. Exactly. Good job. So that's exactly right. So the first thing, well, the most important thing is to laminate the iron core. So what that means is, let me rub these out. Oh, it's gonna take a while. I'll just rub some out so I have more space. Okay. Okay, let me go back to my pen. So essentially, this is the iron core. What we want to do is we want to make these iron cores sort of separated from each other. So kind of hard to indicate, but something like that. Right. So what that means is before, the eddy currents will flow like this. And this. These are eddy currents. But by laminating the core, now they can only really flow like here, small. They can't really flow around the whole surface. They can only flow like this. Okay, and that's going to reduce the amount of magnitude of the eddy currents, which reduces a lot of heat loss. Okay, another modification we can make is any of the ones you actually listed there. Coaster cooling systems, kind of iron core to reduce eddy currents, or using soft malleable iron core. Okay, some other ones include using a thicker wire in primary coil to reduce the resistance and therefore reduce the current, which also reduces heat loss. But the main thing I want to talk about here is this laminated core here. Okay, laminated core here. Cool. So I think, let me just check. So we have 5 minutes. I'll open up the panel to you guys for any questions. But if you guys want, just let me know in the chat. I can try and pump out this last question in the next 4 minutes. Then you guys have a 5-minute break. Yeah, there's like 2 more questions. Actually, kind of want to do this one as well. I'll briefly explain this one maybe as well. But you guys let me know if you have any questions, or I can quickly explain this long response in there. Anyone? Otherwise, I'll just briefly explain this question and then I'll give you guys a 5-minute break after this.
I think go ahead and explain.
Okay. Yep. Sweet. So this question I did in the HSC and I had a really clear memory of this. And the reason why is because there was one particular concept that if you identified, you pretty much got most of the marks here. And I don't know if you guys have done this question. I'll give you guys like 30 seconds to type what do you think the concept is, or the most important factor here is. So rope connects a mass on the horizontal surface pulley attached to the electric motor as shown. Explain the factors that limit the speed at which the mass can be pulled along the horizontal surface. 30 seconds. Would it be the torque and the load? Oh, very close. Torque and load is definitely a huge factor, but there was one factor that like contributes a big part of this, and you have a lot to explain. 10 more seconds. 10 more seconds. Okay, so the concept I want to talk about here is back EMF. And I wasn't sure how much you guys are familiar with this, but maybe I'll just explain back EMF in general, because I think this is a concept that a lot of people forget to revise, and it's quite important in HSC as it's tested a lot. Okay, so I'll start with explaining what back EMF is. So let's say we have a motor. Q&A here. Friction too. Yeah, for sure. There's a lot of factors such as friction, the mass of the block, the motor speed, the torque, and back EMF. Okay. So let's say we have a motor, we have a DC motor that's causing a coil to rotate in a magnetic field, right? And it's rotating because it's experiencing a force from the current. Okay, but as the coil is rotating in the magnetic field, do you agree that the coil is experiencing a changing flux? Coil is experiencing a changing flux. Coil is experiencing a changing flux is going to generate an EMF, right, in the coil itself. It can generate an EMF in the coil itself. Maybe I'll draw a picture of this. So let's say we have a coil like this. We have a just simple diagram. This is rotating this way, and then we have a north and a south here. Okay, so this coil is rotating. It's going to experience a changing flux because it's rotating in the magnetic field. It's going to generate EMF by Faraday's law. Okay, and this EMF is going to be the back EMF. And what that means is it's in the opposite direction of the supplied EMF. Okay, so what this means is when we have a back EMF, it's going to limit the ultimate speed of the motor, because let's think about it. If the back EMF is in the same direction of the supplied EMF, what's going to happen? It's going to go quicker and quicker. And the quicker it goes, the more EMF it generates, the more back EMF it generates. It's going to go to infinity. And the motor is going to be rotating at infinite amount of speed. That's impossible because that violates the conservation of energy, right? So therefore, this EMF is in opposite direction to the supplied EMF, and that's why we call this a back EMF. Okay, so the equation or the mathematical model here is I net is equivalent to E supplied minus E back over resistance. So E supplied is just a number, arbitrary number we have in the very beginning, and the E back will start to increase. Right? And the reason why for that is because initially the motor will start spinning at a certain speed. It's going to increase, and as it increases, the back EMF will also increase. Right? And as the back EMF keeps increasing, when these two factors becomes equal, what's going to be our I net? It's going to be 0 as well. right? And if you have a I del of 0, F equals to BIL sine theta. Current is 0, force equals to 0. If there's no force, there's no acceleration. If there's acceleration, there's no more changing speed. It's going to be constant speed. And this is the point where motor reaches maximum speed. Okay, does that make sense? So one more time, quickly. Back EMF is caused by the wire rotating in the magnetic field. It's going to experience a changing flux. By Faraday's law, it's going to experience an EMF and therefore a current. And then this EMF is going to be in the opposite direction to the supply EMF according to the conservation of energy, right? And then as the coil starts rotating faster and faster, back EMF will increase to a point where it's equivalent to the supply EMF / voltage. And then that will make us have a zero current. And with a zero current, we're going to have zero force. With zero force, we're going to have zero acceleration. Zero acceleration, the motor is not moving anymore, not accelerating anymore. Therefore, with constant speed, and that's the maximum speed the motor is operating in. And that's why it's a big factor, why it limits the speed at which the mass is pulled. Because when it reaches the maximum speed, it can only pull the mass in a certain amount of speed. It can't increase anymore. So the speed of the mass can be put is limited by the back EMF. That's the ultimate sentence you want to say after you explain all the back EMF stuff. Okay, cool. Let me just see. Okay, so I have no questions. So should I give them a 5-minute break, Emma? It's been an hour now.
Yeah, give them a short break and put in any questions. If you have anything about how the exam works or your ATA or anything like that, put it through as well. It doesn't have to be directly about physics.
Yeah. You guys can ask anything regarding exam techniques, ATA, anything about me, how I was feeling for the exam, or anything like that. How to best prepare, when to study, any questions in general. Happy to answer. But otherwise, feel free to have a break. Yeah. Now I'll quickly grab some water, and I'll be back in 20 seconds. Okay, any questions at all? Any questions regarding HSC? Or study tips or exam techniques? Actually, I have a question for you guys. Maybe in the chat, type in what do you guys do in 10 minutes reading time? Here we have a question. Do you think the exam will be more math-based or concept discussion-based? 2019 and 2020 HSC papers vary greatly in those aspects. Yeah. Oh, that's a good question. I can answer you for sure that HSC from now on, since 2019, is going to be very conceptual, right? It's going to ask you to apply concepts into different scenarios, okay? And by doing all the HSC questions in 2019, 2020, it's going to prepare you well. But math-based or concept discussion-based, it's definitely going to be more concept discussion-based. The reason why is because in the concept discussion, you have to use mathematical models to explain your answers, such as just then the back EMF, or if you talk about friction, you have to bring a little bit of content in year 11 about force equals to coefficient of friction times normal. So you can bring another element of the table's friction, right? So it's going to be more concept. It's going to be you understanding concept to a deep level and then utilizing that concept to apply to different scenarios. So it's going to require you to think outside the box a little bit. And then with pure calculation questions, it's going to be a lot less. For example, just asking you to calculate the force on the motor using F equals BIL sine theta. Anyone can do that, applying the numbers, okay? But they're going to make you think about the concept more. best way to approach the exam, i.e. multiple choice first or short answer or calculation. Okay, Costa. So with this, it's best for you to find your personal way, but a lot of the times people don't do the paper in chronological order. They'll start by maybe doing the long responses first because they're worth a lot of marks. But some people would prefer to do the paper from the very beginning. But it just depends. In my HSC, what I did mainly was I started doing the multi-choice first, and then I picked out the questions that I know for certain I know how to do, did all of those, and then tackled the rest of the questions. Okay. Yeah, so the best way is to, I don't know if you've done trials this year, but the trials would have prepared you well for how you would approach the exam, to do which questions first. So Alex asked, I noticed that with the 2021 trial independent paper, there was only 4. Yeah, exactly. NESA's making all the sciences very conceptual based. And I don't know if you do chemistry, it's the exact same with chemistry. They put a lot of conceptual questions in there. And with physics, it's going to be the same this year. So expect concepts such as back EMF to be tested, because those concepts are the ones that can be targeted. Back EMF, something I'll be talking about later will be stars life cycle, and how exactly they transition from one to the other. Okay. But yeah, for sure, keep practicing like the different concepts and understanding to a deep level instead of just knowing how to use the equations. I'll skip the last 3 questions of multi-choice and leave them to the end, as they usually take the longest time for only 1 mark each. Yeah, for sure. Last 2 questions are hard in multi-choice. For sure. Emily asked, what is the best way to learn all the content/theory? So the best way for you to learn content is, well, I don't know how much notes you've taken in class, but the textbook is your best friend. Whenever you're uncertain, just go back to the textbook and then read the stuff and do the examples there. And then, so what I do normally is I would always review all the content first. I'll make sure I understand everything, right? After that, I'll start just writing questions. Okay. And for me personally, I forget the content easily. So like before HSC, before physics, specifically, I went through the textbook and my notes first, maybe write down some of the stuff. So something I like to do is, I can show you guys what I do is, I know the bad concepts that I know the concept I'm bad at. So what I do is, for example, back EMF, I'll just get a blank piece of paper, right? Back EMF, right? And then I look at the notes first, understand what it is, and then close the notes and then write down my understanding of back EMF here. So I have dot points, writing it down. And by doing that, if you're able to do it, that means you fully sort of cover that concept. Okay, you've covered that concept. In terms of like other concepts, I think the best way is to review all your notes first, but definitely do not neglect doing questions, because especially for HSC now, they're going to be putting a lot of conceptual questions in there that you need to be able to use the understanding of your concepts to apply to the new scenarios. Okay, to new scenarios. Yeah. Cool. I think that's all the questions. If you guys have any other questions, feel free to chuck them in. I'll answer them in the 5 minutes we have in the next content block. Cool. So I'll start going through module 7 now. So let's go through this first multi-choice. I'll give you guys, I won't give you guys too long, 1 minute to do this question, 1 minute. Just because we a little bit short on time. So which graph correctly shows the relationship between the surface temperature of the black body and the wavelength at which the maximum intensity of light is emitted? So another 30 seconds. I was just thinking another point for you, Emma, is was it Emma or Emily? Sorry, Emily, is that there's a sort of different dynamic between module 5 and 6 and 7 and 8. So for module 5 and 6 is more concept/calculation based, right? Specifically in module 6 with the induction stuff, you need to understand exactly how induction works to deep level. For example, you need to understand what flux is, you need to understand how does changing flux lead to a EMF and that sort of stuff. And then you need to learn how to use the different rules to derive the formula and direction of the current induced. Okay, so module 6 and 5, I recommend doing more questions, more question-based, just getting exposed to a wide range of questions. Okay, and then for module 7 and 8, it's more content-based, right? Specifically for module 8, there's heaps of theory. And I think actually, there's only theory actually. There's stars, there's the history on atomic models, and there's some particle and accelerator stuff. And there's Big Bang Theory. So 4 things, all content. So for module 8, I recommend you sort of reviewing your notes and then memorizing them. But for module 7, it's a bit of both. There's a bit of history on light, and then there's also calculations on diffraction, there's calculation of photoelectric effect. So there's a combination of both there. Okay, so I guess to approach your study, sort of change the way you will approach 2 modules and the other 2 modules. Okay, cool. So we got 2 responses. One chose A and one chose D. Okay, so this question is testing us on which formula we'll use to sort of identify this mathematical relationship. Okay, so there's formula on the formula sheet, which is talking about the relationship between temperature of black body as well as a wavelength. And this is called the Wing's law, which tells us lambda max is equivalent to Wing's constant over temperature. Okay, and as you can see, lambda max and temperature are inversely proportional. So as one increases, the other one decreases. So the model that will best represent this is this hyperbola here, or this model here, that if you see as temperature increases, lambda decreases. Okay, and vice versa. As temperature decreases, lambda will increase. Okay, so A is the answer here. Okay, cool. Let me go next question. So this is a question on polarization, which can also be a target area in HSC. So have a go at this question. Give you guys another 1 minute to have a go at this. So what I'll do at the end is, since you guys asked about the exam quite a lot, I'll write down some topics for you guys to revise and look into that I think might be really accessible in this year's HSC. Yeah, so another 20 seconds maybe if you guys have got this question. Okay, so we have 2 answers that chose option A and 1 that chose option D. Okay, cool. So there's 2 components to this question. First component is determining the value of IB on IO. Second component is determine which model of light was demonstrated, the particle or the wave model. Okay, so essentially the equation here is I equals to I max times cos squared theta times cos squared theta. Okay, and what we need to do here is, maybe I'll actually first explain what IO and IB mean. So IO is the intensity of light after the first polarizer, and after any single polarizer, the first ever polarizer, it's always going to reduce the intensity to 50%. Okay, so IO is 50% always. That's for any sort of polarization question. After the first polarizer, always going to be 50%. That's just a rule. Okay, so we need to find IO over IB. So what this current here, what this I here, is the intensity of the light after the second one. So this is actually IB. Okay, this is IB. So with this equation, we always calculate the intensity after the second analyzer, what's called an analyzer here. And the I max here is IO in the question. which is after the first polarizer. Okay, so in order to do this, it's actually kind of handy because we need to find IB over IO, and in the equation we've got everything already. So if I rewrote this equation, I can write this as IB is equivalent to IO cos squared theta, right? So then if I want to find this, I can just move IO over, and it just equals to cos squared theta. Okay, and if you plug the angle, which they said here is 30 degrees, right, into the calculator, you actually get 0.750. Okay, so that instantly ruled out C and D. So now we just need to determine if it's model of wave model or particle model. Okay, wave model or particle model. So with polarization of light, we're talking about the electromagnetic waves that are being transmitted. Okay, so the concept here is the fact that we have oscillating electric and magnetic field. So this is the axis, but kind of hard to draw in 3D. Right? So we have E and B and E and B. And the reason why this analyzer can decrease intensity is because it cuts out a portion of the oscillating magnetic or electric field, right? And what is this? What is a oscillating magnetic and electric field? What is that? According to Maxwell's predictions, an oscillating E and B field is equivalent to EM waves. EM waves, okay? Electromagnetic waves. And that is how we can determine it's the line model. Oh, sorry, it's the wave model. It's the wave model. It's the wave model here. And that's what gives us option A. Okay? Cool. Would have any questions? I'll move on to the next one. So last multi-choice before I get into some long responses. Yes, I'll give you guys another 30 seconds because I do want to get through at least one response, long response with you guys. Yeah, so I'll be strict this time, 30 seconds. Okay, that's time. That's time. Do you want to bring up the answers, Emma? I have 2 votes, A and B. Okay, very close. Those are the 2 answers that you would be choosing between when you're actually doing the question. So this question is actually quite straightforward. By looking at the graph here, we have a frequency of 8 times 10 to the 14. So that's here, right here. So what we need to do is interpolate off the graph. So with this one, we have intensity of around there, right? And then with the other one, if I interpolate off here, we have a high intensity. And that's why compared to the photoelectrons emitted from metal X, photoelectrons emitted from Y is going to have a lower maximum velocity. Okay, and the reason why for that is because what's the kinetic energy formula? Half mv squared, right? K equals to half mv squared. A decrease in K is a decrease in V, right? And by having a lower kinetic energy, we have a lower velocity, and that's why X will have a higher velocity, and Y will have a lower. Okay, cool. Okay, we have this question. I already sort of briefly talked about this, so actually I'll skip this one. I'll talk about time dilation. Talk about time dilation, which is quite an abstract concept in physics, HSC. So question here says, outline a thought experiment that relates to the prediction of time dilation. Okay, cool. So there's 2 experiments, one for time dilation, one for length contraction, but I'll talk about time dilation here. So the thought experiment that was taught to all of us was the fact that we had a person in a train traveling at a relativistic speed, so close to light, so something like 0.95 C. Okay, so how this works is we have one person in the train, and I'll draw the diagram here. Train here, we have an individual, we have a mirror here, and he's holding a torch. Okay, here's a torch. So what happens is he shines his light onto the ground, right? And while the train is traveling, this light gets reflected up to the top mirror, and it gets reflected down. Okay, gets reflected down. So from this person's perspective, inside of the train, what he's gonna see is he's gonna just see the light go straight up and straight down in a certain amount of time. Okay, in a certain amount of time. And then we also have another person on the platform watching. So this is a platform. And what he's gonna see is he's going to see when the light gets shone onto the bottom mirror, right? It's gonna go up. But as the light is going up, the train is also moved a certain distance. So instead of him seeing this, the person here is gonna see something like this. Because the train, instead of being here now, train is like here. So he's gonna see this diagonal arrow here. Okay? And same thing, when the light reflects back, the train has traveled a further several, I don't know how long, but how much distance, but a huge amount of distance. But he's gonna see something like this. Right? So we have a distance here traveled. Right? Distance here traveled. So how this explains time dilation is the fact that with different angles or different reference frames, or a different frame of reference, which is a better word, I think, they're going to observe different trajectories of the light being shone through or shone reflected, and that's going to explain a longer time. So this person on the platform is going to observe a longer time for the light to travel up and down because it's traveling a long distance. The distance, speed, and time. Okay, distance, speed, and time. And that's the thought experiment here that relates to the prediction of time, because it's traveled a longer distance in the same certain amount of time. Okay, but that's impossible, right? So that has to mean that time has been longer for the person observing on the platform in order for the light to travel the same amount of distance compared to the first one. Okay, from the first one. So this thought experiment, you can call it reflection mirror thought experiment. Okay, cool. Next question is outline experimental evidence that validate the prediction of time dilation. Okay, so the first thing that comes to mind is definitely muon. So I'll explain a little bit on muon, just verbally, just because of short time. But essentially, muon is this sort of particle that is in space and travels down to Earth, right? And what happened was scientists on Earth did not expect muons to be able to reach Earth because of their lifetime, because they decay while going down. They have only this certain amount of lifetime, right? And before they even reach Earth, they already decayed fully, right? So from a muon's perspective, they won't be able to reach Earth, okay? From a muon's perspective. But from a scientist's perspective, because the scientists are in a different frame of reference, they're gonna experience time dilation. And what that means is they're gonna see a longer time from for the muon to travel from space down to Earth. And they actually found evidence of muon reaching Earth. And this was really surprising because scientists predicted that it's impossible for muons to reach Earth, right? But it actually is possible from the scientist's perspective, where time dilation happens, where the muon will have a longer time because of the frame of reference from the scientist's perspective. Okay, and something else you can talk about here is the atomic clock. So let's say one of you guys jumped in a plane that's traveling at relativistic speed, okay? And you guys travel there for 1 day, right? And what this means is, from my perspective, you guys have a longer time. So that means our age. If that makes sense. Yeah. So our age. It's quite an interesting concept that you guys can look into, but I think the best evidence to talk about here is muon, talk about time dilation. Okay, cool. We have one more question, but I do want to open up to discussion for you guys. Do you guys have any questions? How do you answer? Just like before, you guys asked about exams and stuff, all that sort of stuff. How do you answer? Because it's meant to be a exam technique / preparation for HSC, not just content and concepts. So yeah, you guys 3 to 5 minutes to ask any questions, and then we'll move on to the final module. And after that, I'll write down some key concepts for you guys to review over the next 2-3 weeks for the HSC. Yeah, so one thing I'll talk about here is maybe in reading time, what I do normally is I'll go through the whole paper, get a sort of overview of how the paper is, right? Because you'll be to a point where you read the paper and you're gonna already understand how many questions you can do, and you're already gonna identify which questions are challenging. And you sort of get an overall summary of how the paper is. And then after that, what I do is I don't normally go and start doing the multi-choice. I start structuring my long responses. So all the questions range from 7 marker to a 9 marker. I start planning some of them in my head. So I use example for the motor question, where we had to talk about the factors that limited the motor speed or how fast you can pull the mass, right? So in my head, I'm thinking about all the factors already. And then I'll think in my head the sub points to talk about. So for back EMF, I have a box, talk about 3 things. One is one is what it is, and then how it limits speed, right? And I have another subheading, friction, and then some dot points. So I'm planning out these in my head. So when I get to the actual question, doing it, I'm already just writing my answers down instead of still thinking about what to do. Okay, because long responses, if you don't plan well, you're gonna end up like just writing whatever's in your head, and that's not gonna be beneficial for your long responses. So I definitely recommend, if you have spare time in your reading time, make sure you start planning your long responses, even if it's just brainstorming some dot points in your head and utilizing these subtitles and subheadings in your answers will definitely enhance how you structure it. Okay. So no questions, I see. If there's no questions, I'm happy to move on to last module. Okay, let's move on to module 8. Cool. Okay, so first multi-choice is here. I'll give you guys 2 minutes to have a go. So keep in mind, module 8 is very content heavy. With these questions, if you guys sort of forgot on the content, don't worry about it too much. You can sort of review the content and get the information pretty quickly, which is different to module 5 and 6, where you have to constantly do questions in order to understand the concepts. So 1 more minute. Have a go at this question. Pure content question. This is a pure content question. Yeah. Okay. So we have 3 responses Oh, chose C. That's exactly right. Spot on, everyone. That's exactly right. So I'll quickly explain this then, since most of you guys are already familiar with this. But essentially, Geiger Marsden's experiment was to discover the nucleus that in an atom, in an atomic model, there's going to be a very dense nucleus in the middle that consists of positive charges. Okay, so this experiment is based off plum pudding or Thomson plum pudding model, where it's something like this. As you can see there, this is like sort of similar to this one, right? So that's based off his model. And then if they were to shoot alpha particles into those atoms in the gold foil, right, they're going to expect most of them to cross that the atom because of the space around the protons. They're going to be able to cross through. However, the experimental design or evidence showed that 1 in 8,000 alpha particles reflected back, right? And that is what led to them discovering that little center nucleus in the middle that's causing them to deflect back because of its density that can't allow them to travel through. Okay, so based off Thomson. Yeah, cool. Next question, another theory question on Bohr's atomic model. So give you guys 1 minute. Bohr's improved on Rutherford's model of the atom. Which observation by Bohr provide evidence supporting the improvement? So another thing worth mentioning here is I remember for the HSC, there's going to be questions that's going to ask you to assess the atomic model or the timeline or the history of atomic models. In the traditional way you will structure an assess question is to have pros and cons and judgments, right? But since in module 8, it's more of a model leading to another one. There's not really pros and cons for the models. It's more of having this model, we discover something new, leading to a new experiment, leading to a new finding, and then leading to a new model. Okay, so it's not a pros of a scientist that they've discovered this or that they've came up with this model. It's just the process where they have came up with this model in their time, but this was disproven or improved later on. Okay, so when you get a assessed question, all you need to do is list out each of the scientists and their models, discuss their implications, discuss what they mean, discuss the experiments and their results, and then talk about how the next model improved on previous models. Okay, that's just a tip for module 8 questions, long responses. This might come up in HSC where they just ask you to describe atomic models. But if you see assess, you don't have to structure answers using pros and cons and judgment. Yeah. Okay, we have 2 answers. Both chose A. That's exactly right. So Bohr's model was a huge improvement to Rutherford's model, especially with Bohr's 3 postulates. And one of the postulates was talking about the emission spectra of discrete wavelengths, where he talked about electrons in discrete energy levels. So electrons in these discrete energy levels, and they were able to jump up and down, right? And these the jump, especially when it comes down, is going to emit a wavelength of photon, a specific wavelength of photon that's corresponded to the energy required to jump up. Okay, and that's why it gives us A. The rest of the options either is not Bohr's contribution or just doesn't make sense. So A is the right answer here. Okay, cool. One more question here, which is a decay question, which I thought was kind of interesting, because decay sometimes gets neglected a little bit in people's revision. So I thought this would be a good question for you guys. So another 2 more minutes for this question. and then I think we move on to long responses. Okay, so we have two answers, both chose B. Okay, cool. That's right. So for this question, the formula we're going to use is the formula in the HSC physics data sheet. And I pull that up quickly. We actually have this formula. NT is equivalent to ln2 over T a half. And what T half means is the half-life. So half-life is the time it takes for the particle to lose half its mass. Okay, so that's half-life. So any sort of particle, we often associate them with a half-life because that's just a good unit or good timeline to quantify the timeline of a particle. Okay, so once the half-life, we're able to use this equation to calculate the decay constant. Oh, sorry, this isn't NT, this is lambda actually, that's the decay constant. Okay, so all we need to find is the half-life of this particle. And by looking at the graph there, we can see the half-life or the initial mass of the particle is 400 grams. So the half-life is when it loses half its mass, which is 200 grams, which is around here, and it's 100 years. Okay, 100 years. So if we do lambda equals to ln2 over 100, and as you can see, be careful of the units here. The reason why is because the question asks us in years or in per years. That's why we don't need to convert this 100 to days or seconds. Actually, most of the time it's seconds. Normally we'll have to convert this to seconds by timing this by there's 100 years, 365 days times by 24 hours, and so on and so forth, all the way to seconds. So just be careful of the units in all these questions, and you have to know when to convert or not. And then if you plug in the value there, it'll give you an answer of B here. Okay, answer of B here. Cool. Okay, let's move on to long responses. So we have this particular question here, which is a question in my HSC. It was kind of challenging as well. I remember doing it. So let's have a read of this together. So in the experiment, alpha particles were fired into a thin sheet of beryllium. Unknown radiation was detected. And then you have the diagram there. Further experiments were conducted in which it was observed that the unknown radiation was not deflected by an electric field. Number 2, caused protons to be ejected from a block of paraffin. Number 3, could not produce a photoelectric effect. All right. And the scientists debated the nature of this unknown radiation, hypothesizing that it was gamma radiation. And what we have to do is to explain why the hypothesis was proposed and then rejected with reference to the observations. Okay, reference to the observations. So let's start by sort of identifying what this what this experiment actually is trying to do. I think I see a question in Q&A. When will we get the recording? I think Emma, would it be straight after this? Will be uploaded to YouTube?
I'll just type the answer.
Okay. Yeah. Yeah. So I'll give you guys the option here to type in the chat to answer what exactly is the experiment trying to do. What is the goal of this experiment? Once we identify that, we're able to continue with our answer. What is the experiment trying to do? well, what did this experiment achieve from the theory we learned? Anyone? Okay, that's all good. So this experiment is where scientists were able to discover neutrons. So discover neutrons. Okay, so what they did was they bombarded alpha particles into beryllium, and that were able to eject protons off the beryllium outwards, right? And then this is sort of this unknown radiation that ejected protons off a block of paraffin. So here we have a block of paraffin here, and we're able to measure protons being ejected out of that from the unknown radiation. Okay, so with this question, what we need to do is need to make reference to all three of the observations there, okay, and talk about why it was initially accepted but then was disregarded after, okay, or rejected after. So the first thing, let's look at it. So it says was not deflected. So this unknown radiation was not deflected by an electric field. What does that mean? So what makes this it'll be deflected in an electric field? Deflection means force, right? Equals to QE. We have electric field, but we need charge, right? If it's not deflected by the electric field, that means charge is zero, right? So the gamma rays, right, was not deflected by E field, and would not consist of charged particles, right? And this proposed here is aligned with the gamma, the properties of a gamma ray. Gamma rays don't have any charge at all, right? And this is the reason why. So you can do an arrow here in your answer. Thus, why it was accepted or proposed. Okay, because scientists knew gamma rays didn't have any charge, and for this unknown radiation to not be deflected, it was aligning with what they knew, right? So that's why they will propose this. Okay, so now let's look at the second dot point there. So cause protons to be ejected from a block of paraffin. Okay, I think it's better to look at the third one first, because we want to use that second dot point there to sort of summarize our answer, because the end result is the fact that protons were ejected from the block of paraffin. Okay, so let's look at the third one. Third one talks about could not produce the photoelectric effect, right? So can gamma rays produce photoelectric effect? What is gamma ray? Are gamma rays high radiation energy or low radiation energy? What are they? They're very high energetic radiation, right? They're the highest from alpha rays, gamma, beta, and gamma. Gamma is the highest out of all of them by far. Okay, so however, it wasn't able to produce photoelectric effect, right? Which was not the property of gamma rays, as gamma rays were high in energy, which would have ejected electrons. Okay, so like that. And that is what led to the initial rejection of this proposal as a gamma ray, or as saying that the under radiation is a gamma ray. Okay. So the third point here is cause protons to be ejected from the block of paraffin. Okay. So the reason I wanted to put this third is because for them to discover neutrons, they measured protons being ejected out of the paraffin block, which is how they sort of discovered neutrons. Okay. And the reason why gamma rays wasn't accepted was because gamma rays are high energy radiation, but they don't have any mass or momentum, right? If you think about it, if you have a ball in front of you and you have super high energy, if you have light, if you have a torch, if you shine a torch on the ball, would the ball move, right? The ball wouldn't move because the light doesn't have any momentum or mass in order to move it, right? So that's why gamma radiation couldn't be accepted, because they didn't have the mass or momentum to move that protons or eject the protons out of the paraffin block. And that's the reason why they proposed this new thing called neutrons, which has some sort of mass. Okay, so I'll write a quick dot point here. Gamma rays have no mass and momentum, which means they cannot eject protons, opposing the experimental result. Right, and then you'll do something here saying overall the gamma rays, the initial gamma ray wasn't deflected by electric field informed scientists proposal of gamma rays being this under radiation. However, further experimental results such as photoelectric effect and the ejection of protons were able to indicate that this wasn't the case, and therefore rejected the proposal of under radiation being gamma ray. Okay, cool. So that's this question. Definitely pretty challenging. Had to know some properties on gamma rays, which definitely gets neglected quite a lot. So this is a good question to look at in your revision before your HSC physics, especially memorizing some of the properties of gamma rays, such as high energy radiation, no mass, no momentum, and it's also high energy photons. Okay. And then also have this last question here. How did these experiments change the model of the atom? So I'll just briefly talk about this. With this discovery of the neutrons, it led to Rutherford's model. Okay, it led to Rutherford's model, where he talked about the planetary electrons rotating around the nucleus. Well, not even planetary, he just placed electrons around the nucleus. But the most important thing with Rutherford's model was he proposed a nucleus. Okay, so proposed nucleus. Okay. All right, I think we have one more question to go, and then we have five. Well, actually, we have two more questions to go. Let me see what the next question is. Oh, oops. Present. I have a calculation question. Yeah, I'm probably gonna skip this and talk about star's life cycle, because I do think this is quite important. So, what I'm gonna talk about in this little bit here is not a question. I just wanted to discuss this a little bit. So basically, a star starts forming. A star is formed by the gravity in the universe attracting all the different gases, elements, dust, all that sort of stuff into one little ball, and that's how a protostar is formed. Okay, and the protostar keeps developing into a main sequence star. And what I want to talk about is the main sequence star, its operations, its process, and how it transitions into a red giant. Okay, so I'll write up a sample response for you guys here, I think, while explaining. So, so this is, oh, why is it not letting me again? Do green. Okay. So this is star's life cycle. Okay. So when a star in its main sequence stage when a star is in its main sequence stage, it fuses hydrogen into helium. And there are two processes for this. Does anyone know what they're called? You can rapid fire in the chat. There are two ways hydrogens are formed into helium in a star. Obviously, anyone to answer. I'll give you 20 seconds. Fission fusion. Fission fusion, not quite. Fusion is the process, but I was looking for the specific process, and this other person is a CNO cycle, CNO and proton-proton cycle exactly, right? So it's actually a CNO cycle and proton-proton chain. Right, and these two have their specific processes you guys can look into, and the important thing here is to memorize the formula. So I'll just write down. Okay, memorize formula. Okay, so the next thing is, so this is going to continue to happen in the main sequence star, where the hydrogens are fusing into helium. Okay, so when hydrogen fuel is used up, the star will begin to collapse. Due to the inward gravitational force outweighing the outward pressure force. And why is this? So what this means is when the hydrogen fuel is used up, so hydrogen fuel just means hydrogen in general in the star, because they're all fusing together to helium. What used up means is just there's like not much hydrogen left. Well, there's no hydrogens left. So when the hydrogen fuel is used up, the star will begin to collapse on itself due to the inwards gravitational force outweighing the outwards pressure force. Why is this the case? The reason why for this is because when fusion is happening, do you agree that there's going to be heat produced and pressure produced from the process of CNO cycle and proton-proton chain, right? As they produce energy radiate outwards. Going outwards is pressure force going outwards and heat force going outwards, okay? And that's the reason why during a main sequence stage, the star is able to maintain its composition or maintain its shape, because we have an outwards force from the fusion process. We also have an inwards force from the gravitational process, okay? And those two balances out. But when hydrogen fuel is used up, there's going to be a lack of fusion now, right? So outwards pressure force due to a lack of fusion occurring, right? Which in bracket, which creates heat and pressure necessary to sustain gravity. Okay, so that's what's happening. And after this, I'll move on to here. Then the extremely hot helium nuclei which was built up during the main sequence fusion. So in the main sequence stage where they're fusing through CNL cycle and proton chain, they're fusing into helium, and these helium are going out to the outer bound of the star. So what this looks like is something like this. This is hydrogen, and then it's forming a layer of helium on the outside. Oh, it's bad. Something like that. Okay. And then after hydrogen is finished fusing, we have a whole layer of helium on the very outside. Okay. So the next thing is, with sufficient mass, the star's gravitational force will be able to sustain the density necessary necessary for helium to fuse into heavier elements. Okay, so once hydrogen process finishes, we're gonna have to look at the mass of that star when it finishes hydrogen fusion, right? And if it has sufficient mass and density, it's gonna allow helium now to form into heavier elements. Okay, and this process commences as the helium flash. Okay, resulting in the star expanding into a red giant. And this is how the process of star works. Okay, so when hydrogen fusion finishes, you can have a nuclear helium nuclear outside on the surrounding core, and then with sufficient mass, it's gonna allow helium to fuse again. And when it starts fusing, it's gonna expand, right? Because we have more pressure now, more force, more heat force now, right? It's gonna expand, and when it finishes fusing helium, the same process happens exactly as what happened in hydrogen. Right, and it's gonna keep fusing the heavy elements, and depending on the size of the star, it's gonna either stop at a certain element, or it's gonna keep fusing until iron, which is the last element it can form or it can fuse. Okay, so sometimes what the way I explain this is I'm explaining this using like a contract and expanding like motion of a star as it fuses from lower elements to higher elements. Okay, cool. So that's all from the star area. Do you guys have any questions? It's 2 o'clock now, so maybe I'll give 5 minutes for any questions at all for today, and then I think we'll end it there today. I also want to know how you guys are feeling for HSC. Maybe Emma, if you do the poll up again, we'll just say A is confident, B is somewhat confident, C is not too confident, D is like completely not confident. Just want to see how you guys are feeling for the HSC, and then open up for any general questions at all. Type it into Q&A, have you answer. And I hope this really helped you guys today. Try to pick out the key concepts, key topics, and identify some of the niche topics that I think might be assessed in HSC. So yeah, fill out the form, see how you guys are feeling. And B and C, okay, we have 2 people feeling somewhat confident, 2 people feeling not too confident. That's all good. You guys still have 4 weeks, 3 weeks to pump this out. That's a decent amount of time to smash all these content out, I think. Yeah, Let me see if there's any questions. I don't think there's any questions now. Yeah. Well, wait. Okay. Emma, you happy to let them go now, or?
Yeah, if anyone wants to ask anything, we'll give it another like 30 seconds, but let's just say thank you so much to Galen for his time. And yeah, if you have any more questions, we'll stick around for another couple minutes, but happy to let you go.
Oh, it's mainly memorizing the concepts and laws. Yeah, Alex. It's especially true for module 7 and 8. Like module 7 and 8, it's memorizing content, heaps of content, like memorizing all the models, all the transitions, all the experiments, all the results, how one leads to the other. And the laws and concepts, I think, comes through practice. Like with me, when I was doing HSC, as soon as I look at a question, I already know which concept they're testing. I already know the law, I already know the formula. I didn't really have to look at the formula sheet much because of the practice. Yeah, so definitely memorizing for sure. Module 7 and 8. Yeah. Any other questions?
Okay, awesome. I think we'll leave it there. Thank you so much for coming. You'll get an email in about 10 or so minutes with some information if you want to request Galen as a tutor, and also about where you can access the recording to rewatch anything you missed. Thank you so much for coming, and we'll end it here.
Okay. Thank you guys for coming. And again, study hard. You guys got it. And maybe we'll see each other in the future. But yeah, thanks for coming.